Welcome to this afternoon's session, Migrating to Cloud Spanner. My name is Sami Zahour-Din. I'm a staff solution architect with Google Cloud. I'm joined today by Neil from across the pond. We're both going to spend the next 45, 50 minutes with you going over all kinds of scenarios on migrating from digital tape archives to Cloud Spanner. Just kidding, we're not going to talk about digital tape archives to Cloud Spanner. Hopefully that's a different talk. If you need that talk to me afterwards. So most likely you're coming from much more contemporary frameworks, much more interesting database choices. And really what we want to do today is talk about that. I'm going to talk about Cloud Spanner. If you're here, hopefully that's because something externally enticed you to want to look at what a migration would look like. But we'll go over real quick what the background is on Cloud Spanner and why you would want to consider it. We'll talk about, in general, how we've thought about migrations and how Neil and I have put together sort of a sequence of steps that we think applies to most organizations and the way that they're going to approach a migration. But we really want to make it practical for you. We've chosen a couple of case studies that we'll walk through step by step and show how you would go from a source system into Cloud Spanner. So hopefully you'll leave here with something tangible. And then finally, we'll wrap up with some closing thoughts. Hopefully that sounds fair. So a quick background on Cloud Spanner. It's internally used within Google as Spanner. It is our transactional record of state for hundreds of applications. And it was born not sort of in the beginning. In the beginning, Google was busy solving how to index the internet and sort of find all these massive patterns and provide meaningful search. And it wasn't something that was initially tackled until it became critical that we did tackle it based on the size of some of our businesses. But when we did, we realized a lot of challenges that we were overcoming are faced by a lot of organizations. How do you, at scale, maintain a database with high reliability, high durability, transactional throughput, something that can be used in financial transactions? And so Cloud Spanner is the externalization of that. We realized a lot of customers have the same challenges and have gone down different paths to try to solve it. So if you are coming from that sort of, hey, broad use of data, but have had to make trade-offs in the past, had to decide on what you were willing to give up, hopefully this talk will be applicable to you. It's enterprise grade. Google uses it to run a multi-billion-dollar enterprise. We have other customers using it as well. But really, it's designed with a high SLA in mind to be strictly consistent. It is ACID compliant. And it's distributed. It's the thing that a lot of organizations try to challenge, try to solve with distributed architectures, with a multi-server approach, with multi-nodes, with a lot of interconnect and a lot of distributed storage. It is all that, but instead it's just a database behind an API. It gives you all that distributed nature, but you don't really have to do much to get through to it. It's relational in nature, so relational data is sort of like the easiest thing to get your head around if you've been around databases. It's been around for a very long time. It's something anybody can sort of reason about when they go from one team to another. Within Google, we value developer time considerably, and it doesn't make a lot of sense to have developers move from one team to another and sort of have to say, well, what storage are you using? How are you using it? What are their canonical queries? Everybody sort of gets SQL and gets a relational model pretty well, and so there's a very little low friction point to move saliently between teams and say, oh yeah, I know, you're using Spanner at the back end, I can get going on that. And it's horizontally scalable. It's not much. It's not this sort of heavy-handed, you can scale up, but you can't scale down. And it's not where you have to make a capacity request. It's really you kind of poke an API and you get a lot more transactional throughput through to it. To spin it up, it's pretty simple. You name the instance, choose a region, pick a number of nodes, and hit create. I just wanted to show that because I thought it was a pretty cool animation. All right. I didn't make it. So really, you just have to reason about two things, and then I'll turn it over to Neil. And naming in computer science is everything, right? So name, you have to name it, but then you have to pick how many nodes. Nodes is really just your unit of capacity. It is the most sensitive thing to cost. You pick how many nodes you need, and we'll go through kind of what each node gives you in a little bit. And then where do you want it? So how much capacity do you want, and where do you want it? Which region? Do you want multi-region? The product comes in a lot of different varieties. And the last thing is take your code, merge it together with our client libraries, or speak SQL to us, and then you're ready to go. We understand DDL as a database, so things that are used to doing in other databases are pretty easy to use. similar to like BigQuery and other products, there is a built-in query window. So that's the basic. It really takes, what I described takes longer than it actually does to actually get started with Cloud Spanner. So now let's talk about migrations, how we're going to talk about the rest of the programs we're going to walk through in terms of the migration practical examples. Neil's going to talk through that.
So hi there, my name is Neil Markwick. I'm a solution architect from Belgium. And so in this section, I'm going to give a general framework for migrations, giving you a high-level plan of action for migrating your application from the existing database to Cloud Spanner. So the first step, you need to isolate all your database access code. If you've got it distributed in various modules in your application, including in any lines of code, it's best to isolate that all into a separate module. And that will be the one place where you have all your database access code. And ensure that your development team only adds new code in that module. So you know exactly what code talks to the database and exactly what code needs to be changed during the migration process. In general, this is a very good practice because it gives you one single module to test your database interactions. And similarly, it enables your unit testing of your application. You only need one single module to mock out. You don't need to have a test database. You don't need to have some weird and wonderful way of creating some data that takes care of some weird and wonderful edge conditions. You can mock all that out and supply this bad data to the rest of your application to test how your application handles it. It makes it a lot easier to find and analyze any complex SQL queries you've got in your application. And it gives you a single point to add metrics and alerts for monitoring your database access. For instance, you could add an alert for query latency so that you know when your queries are starting to get a bit slow, it's time to resize your database, add more power. Or you see which particular queries are slow, so you then need to dive deeper, find out why they're slow, maybe optimize the query a bit better, change the way things are read perhaps. Also allows you with the metrics to check the frequency of reads to the tables, which may give you an indication of whether you can add some client-side caching to your database layer, thus giving a performance boost to your application because it no longer needs to read from the database and get it from the local cache. And of course, failure alerts. So any read-write failures, any inconsistency problems, you've got a place to alert it and catch the problem before it starts getting really bad. And as I said, you've got a single isolated module for migration. So your next step is to add the code to that module that reads and writes to Spanner. Sounds simple, but we'll look into more details about that later. You'll be reading and writing at the same time as reading and writing from the original database. You would include capabilities in your application that are not available in Spanner. Again, more on that later. And code would be reading to and writing from both at the same time, but you'd have one database as your source of truth. At the beginning, of course, it'd be your original database. And once you've fully migrated your data over and you're sure there's no inconsistencies, you can switch to Cloud Spanner as your source of truth. So when you're writing to a database row, to Spanner, you should update the entire row. You shouldn't just update the columns, and that way you're ensuring that the data you're writing to Spanner is fully up to date. On reads, you can read from both databases and compare any inconsistencies and report those inconsistencies. Again, this is to gain confidence that your migration has happened correctly. And once all your data is imported and everything's synchronized, there should be no inconsistencies and no more failures. One other thing you should be doing, if you do deletions of rows in your database, you should keep a log of these. When you're importing rows might have already been deleted, so you don't want to be recreating these rows you've already deleted whilst you're doing your import. Keeping a log of the deletions will allow you to check whether this row has been deleted when you're re-importing it. And finally, one really useful thing is commit timestamps. Some databases do this automatically. Spanner, it's an option. You have a column which is the timestamp when that row has been committed. And you can use this to know which is the latest data version, whether it's the data you're importing or it's the data that's already been written by your application to Spanner. And also this module, one other thing, allows you to canary the use of your new database. You switch the source of truth partially. You can have some application instances talking to Spanner and some talking to the original database, so that if you catch any problems early, you can roll back. So how would we actually migrate? Well, simple method. You convert your database schema to Cloud Spanner schema and create your database. You shut down your application. You do your export and import whilst your database is not being written to, so it's completely stable, and you start it up again. This is not an ideal path. for several reasons. Firstly, there's no rollback. Your application, if you start noticing after a couple of days things are going wrong, some data's getting corrupted, what do? You can't roll back because you've got a couple of days new data. You can't fix the data. You just start panicking. If you roll back, you've lost the data and you're a problem. And secondly, your application is down. If you're moving to Spanner, it's presumably because you want to take advantage of the scalability and the availability. So you wouldn't want the downtime associated with an export and an import of a large data set. So what do? We want a live migration process. Once again, you start with the same way. You create your database on Cloud Spanner, and you export and import from your original database to Spanner. But this time, you let the application stay running. Now, of course, whilst your application is running, your exported data is already out of date. But that's not a problem, because we'll see. You write to both. You keep the original database as your source of truth and continue updating rows in Spanner. There will still be some inconsistencies, but that's why your original database is still the source of truth. Then, whilst that's going on, you do another import and export of any changes that have occurred since the last export. Now, this will bring your data in sync, provided that you only write rows that haven't already been updated. So you also, at this point, replay any deletions that have occurred. And when this is completed, it should be that your Cloud Spanner database is fully in sync with your original database. And the monitoring that you've added in your database access layer will not be showing any more inconsistencies, will not be showing any more errors. You can repeat this last step as many times as you want. And at this stage, you can also run a massive compare to see if everything's in sync. Finally, when you're convinced everything's good, not finally, sorry, you switch to be the Cloud Spanner as a source of truth. Again, like I mentioned before, you can do this as a canarying process. You can partially switch some application instances or a percentage of the traffic, and then monitor things, see if everything's good, and gradually increase the percentage that is being written to Cloud Spanner. And if things go wrong, you can immediately roll back. Because your original database is still being written, you've got a perfect rollback position to go to. You won't lose any data. Everything's fine. But if everything's gone forward, everything's working well, and everything's fixed, then you can turn off the code that writes to your original database, turn off your original database, shut it down, and you're fully running on Spanner. And at this point, of course, you have your launch party. Hand you back to Sammy now, who will talk about the example from migrating from a NoSQL database to Cloud Spanner.
I really wanted to have the party.
Yeah,
so
later.
Later, OK.
Let me finish this talk.
Let's see. Oh, big button. OK. Migrating from NoSQL. So the obvious thing here is that Spanner is not a NoSQL database. But we have a lot of customers and a lot of interest for customers coming to us and saying, hey, I made these design choices in my application stack a while ago where I couldn't scale in a relational database, a traditional relational database, very easily. And so I had to decide what I was going to give up. And most of the time, organizations chose to give up transactional consistency. Hey, let's give up transactional consistency because then we can shard really easily. Or they decided, you know what, we'll maintain a relational database, but we'll employ some sort of shim, some sort of sharding shim. And so we're not really getting true transactions across the entire database in one context, but we'll have to sort of manipulate it and introduce some plumbing in between. So really the point of this slide is that you can have your cake and eat it too. Spanner takes care of that. It takes care of that ongoing true horizontal scalability while giving you transactional consistency, while giving you the ability to stay high in terms of, to keep a very high uptime. And then it gets you back to a very simplistic model where you're not having to deal with, is this key value, is it document, is it, what is the underlying storage? This is very simple to understand SQL semantics. So when does it apply? So when would you do this? You wouldn't do this for something that is highly volatile in nature. So if you're just keeping track of a key, and then you have an arbitrary number of attributes associated with that, and it's really hard for you to get a grasp of, is there a well-known consistent pattern to the attributes we're keeping track of, with the thought that those attributes would translate to columns, then this wouldn't be a pattern for you to follow, right? This would be really, if you're like, generally we're using it as a way to keep track of certain attributes. The collection or the set of those attributes is relatively static. Maybe some attributes add here or there, but that's OK. We can do schema changes within Spanner. But it's not too It's not too varied. It's not too all over the place. Reasonably high volume. Spanner is a running service, which means you instantiate a certain amount of capacity to it. So if you're only, say, transacting with the database at a trickle volume at some sort of light lookup or something, that's not it. The use cases we're seeing are folks that are saying, I'm wholesale running massively high transactional throughput beyond just a light workload. The source database should have a pretty easy way. I think most databases today will have a pretty easy way to import and export data. So much like what Neil was mentioning, not yet. Much like what Neil was mentioning in the import-export, the migration general framework. And the last thing is it's a real plus if the source system has some sort of mechanism to do the equivalent of change data capture. If you can sort of know what's coming in out of that database, it's great. Some source examples that we're seeing a lot of are folks that are running their own Mongo infrastructure, own Cassandra infrastructure, that also sort of want to get out of that pattern, but also folks coming from more traditional or more service offerings like DynamoDB. So we're going to pick one of these to walk through a migration. Anybody want to take a guess? Right, so DynamoDB. All right. So it's pretty straightforward. It's actually not that complex. DynamoDB is a single table structure. It's not many tables related to one. It has some nice, interesting similarities with regards to Cloud Spanner in terms of the way keys are laid out. But it is a table, and we're going to go through a straightforward path. This kind of aligns very nicely to what Neil was talking about, where we're going to have a bulk loading path that's going to come in through certain export features, and then we'll have our trickle feeding, our streaming path. We'll collate those onto the blue icons are cloud, Google Cloud. We'll basically coalesce those onto the cloud side, bring those together using a technology on our side product called Cloud Dataflow, and then they'll make their way into Spanner. So let's build this together. Homework before you get started is to estimate how much Cloud Spanner capacity you'll use. Generally, there are some rules of thumbs in regards to how much storage should be allocated per any number of nodes. So if you think you'll be strained on the storage side of things, you would need to scale up the number of nodes. And so it's basically a quota system of 2 terabytes per node, 2 terabytes per node. And so if you are going to exceed that, you just want to kind of overshoot that to allocate enough nodes to cover that. If you're well within that, then you're going to design on the side of throughput in Spanner, which is how much transactional throughput do I need, which is the second point. Is so now I know how much storage I have, how much I/O do I have on this database, and then understand the data model. Where am I coming from? So in the case of a DynamoDB origination, Dynamo has a couple choices for how it structures its primary key. Is it hash or is it hash plus range? Like we said in the last slide, then across all my items in my table, what is the superset or the set of collection of attributes so that I can understand how to create my columns? What are the data types of those attributes? And then also keep track of any secondary indexes. This sort of, if you do this as a worksheet or as, like I said, as homework, it sets you up for a nice migration path. First step is understand the differences. The data types are generally there, but there could be some differences. So understand how data types from one map to the other. Generally, you're going to find all the same data types, if not more. But this is the canonical mapping of data types. So let's make it practical. Let's start with a baseline DynamoDB table. This is a table you could create. It's using a simplistic hash key as its primary key. It's not using hash and range, and it's a hash key called username. We have a little bit of provision throughput. And what I'm not showing on here is that in order to facilitate that streaming hook, this table would also have streams enabled, DynamoDB streams, which would just be another flag on the end of this, or you could adjust your table. If you have a table that's already running, you could simply augment it and add streams to it. So let's create the equivalent table. I'm sort of taking that metadata we went through in the homework collection, and we're going to create the equivalent table in Cloud Spanner. And so let's say that we've determined in that source table, we've looked at all the attributes inside of our DynamoDB table and decided that really there's just sort of 4 consistent attributes, or 4 attributes that represent the majority of what we're looking at. It's like zips code subscribed, whether somebody subscribed to a feed or not, when they're sent a reminder date, maybe some points they've earned. So this is a fictitious table, but it's probably not too dissimilar from the way that you would use a simple database, a straightforward database like DynamoDB that's more kind of key value oriented. So we'll map that nicely onto a Cloud Spanner schema. To get to that point, kind of in the beginning I alluded, it's actually really trivial. This is almost the entirety of what you have to get going with in Cloud Spanner is pick where you want it, how much capacity you want, and what you want to call it. If you hit create, and I think we'll be showing this later, if you hit create, it's a few seconds. In a few seconds, you've got that much capacity sitting there. And so in a 3-node regional setup, this is roughly 30,000 reads a second, consistent, and 6,000 writes a second. So that's a lot of capacity, especially when you're talking about maybe dealing with much lower capacity in terms of provision throughput. Just for 3 nodes, you get a lot. And 3 nodes would be kind of the minimum for a production size setup. There's also multi-regional, which implies more quorum copies. I would encourage you to go to kind of a Cloud Spanner 101 talk to understand kind of how the quorum works and where the writes are distributed. But basically, if you do this within a few seconds, you've got a tremendous bucket of input-output. So that table I showed on the previous screen that said, hey, we've analyzed our source table, figured out how it looks in Dynamo, figured out the columns. How do we map the columns to something database-oriented? So within the instance, so in the previous screen, I showed how to create an instance. Within that instance, we can now begin instantiating databases. Databases are sort of logical containers. The instance is a ubiquitous sea of capacity, and then the databases are specific logical units. Inside of that database, you can create tables. Looks and feels pretty much like any other database. It's really not that dissimilar. But we take our DDL, which is standard DDL, plug that in, and we create our database. One thing that we would do at this point in our table is we'd run back to our Dynamo table, and using DynamoDB streams and Lambda, we want to capture all the changes off. And so I would turn around, I would make a function like this, a Lambda function like this, and this becomes the glue between all the changes happening inside of my DynamoDB table and getting it over to the Google Cloud side. And we're using basically PubSub in the middle. So basically what I'm saying is, hey, inside of my Lambda function, every time I get a change, I've got my DynamoDB streams to configure to send me the new image. In DynamoDB, you can say, send me the old image, the new image, or both. And so all I'm doing is I'm taking the entire payload, I'm just shoving it over, and this basically has Lambda make a call and sends it over to PubSub. We'll show this in action in a minute. So it's in PubSub. PubSub is our highly scalable distributed messaging system, in which case you can be pumping messages in at 1 million a second or something ridiculous, whatever your application needs, and have n number of subscribers. They can be pull subscribers or push subscribers, where something is contacting and polling for messages, or it can push to an endpoint, any kind of endpoint, like a cloud function or whatnot. We're going to be using a pull mechanism. This would be an interesting time if your application had the luxury where you may, this would be the inflection point at which you may decide, like, hey, for consistency's sake, let's do a quick pause while we kick off an export. It's not strictly needed, depending on how much data you think is going to be mutated during this time or overlap of keys. But this would be that moment you would decide, hey, we're going to kick off an export. Should we pause writes for a second while so that we can keep track of exactly when this Lambda function was instantiated and when the export was kicked off? It's a momentary thing that you would have to decide. It's not strictly needed. So how do we get data? So we've already put in the Lambda function. That's sending over the streaming data. Basically, now how do we do the bulk? So that becomes our checkpointing time. Like, put in this function. We've started collecting data that's changing as of this moment. Now how do we do the mass export? So you need to lean into the platform that has that hosts that data source. In the case of DynamoDB, there's a tool. You can run a data pipeline job. That is the canonical way to get data out if you were to go and say export. But what it does is it lands that data into an S3 bucket. It kicks off an EMR process, elastic MapReduce process, reaches into the table, and then kicks out flat files that are JSON files and puts those into an S3 bucket. So if you think back to the Lambda function, the Lambda function was our glue that got us from changes happening in Dynamo over to PubSub. If you think about our S3 bucket, the glue that kind of moves it from Amazon side to the Google side is a copy command. Before you do the copy, you just kind of look at the bucket. There should be a success file inside of the export that will tell you that everything went correct. But essentially, you can use the GS util, it's the Google storage utility, that understands how to read Amazon credential files. So this is a very handy feature. that essentially, let's say you're working on an instance or you're working inside a Cloud Shell and you've installed the Amazon command line utilities and obviously now the Google command line utilities, including gsutil. gsutil knows how to read your Amazon credentials if if they're configured on the same box, and you can literally pass it an S3 URL. So in this case, I can say, go from the S3 bucket to my cloud storage bucket and rsync. So just tell me everything that's there. If it's an especially large transfer, we have a background operation called Cloud Storage Transfer Service that will do this for you in the background. And then now both sets of artifacts, both the pub/sub streaming changes as well as the flat files from S3 are sitting, have shown up on the Google side of the fence. So what do we do with those things? The first thing is we do a job to import all those flat files from S3. So we would kick off a Dataflow job. And Dataflow is our managed service for managing Apache Beam pipelines. And so we would have a pipeline written, an Apache Beam pipeline that knows how to take flat files in JSON format and write those into Cloud Spanner using something called Spanner IO, which is a mechanism for Apache Beam to write to Spanner. And that would run through and that would complete. And this is the nice thing about Cloud Dataflow is it takes your Apache Beam pipeline and then gives you this very kind of introspective view into your pipeline, how it is and how much, how many messages are being written, what was the success factor. And so you would monitor the progress, verify item counts. When it's done, perhaps do some selects between the two databases and make sure that the item count between one table and another table are the same. And do some spot checking. Kind of look at an item look at the item in one database and look at the item in another one. You're going to want to do this maybe for different items inside of your database. So now the more interesting challenge, which is how do you get those streaming changes, which have been getting into the pub/sub queue, which haven't been picked up yet, how do we get those out and pushed into Spanner? So now we want to create a subscription to that. Topic and run the same thing, but this is now a streaming job. This will not terminate like the other job, which was a batch job. This is a streaming job that kicks off. And it's very similar. This is a DAG structure, which is like essentially a structure of activities that you've asked to happen in a sequence. And now the streaming pipeline will stay in continuum. It's not going to terminate because you expect messages to keep coming in until the migration is done, right? And what this does, it's slightly different. It's not just new records. It has to look and see, is this a create or an update or a delete? This is because the Spanner API calls that do these are slightly different. And so you need to separate this logic. So I've shown you some Dataflow code. I don't want to make this slide detector. So let's show you some of the background behind it. So let's look at the batch pipeline. It's a little more concise for purpose of demonstration. But this is Apache Beam code. This is a kind of a trimmed down version of the pipeline. You create these pipelines, and you essentially just create these stages within your pipeline. And this is a pretty straightforward one. You can annotate it with sort of a friendly name that will be represented in the UI. But I want to read items. I want to parse items. I want to create mutations and write items. It sounds like kind of the canonical activities that you would go through. And let's look at one of these. Let's look at like parse items, which is basically how do I take that incoming JSON that's coming from the records that are coming from Dynamo, and how do I map those? What is that step that just said parse items in my Apache Beam pipeline? What that's doing is it's mapping it to a Java object in this case. And so you would have some code that just says, hey, map JSON with JSON, and now I've got this object representation of each record that's coming through. So now that I got each record that's coming through, the next thing in my pipeline list was create mutations. Create mutations takes each of these class members now and sort of lets me map them to column names. So this was the second step in that pipeline. And so once that's done, then basically that pipeline has what it needs. One thing I'll touch on is the Dynamo. We mentioned that could have a slightly different primary key structure, which would be hash and range. This is where you would take advantage of a feature within Cloud Spanner called Interleaved tables, where one table can be nested inside of another table by attribution of a commonly shared primary key, or the first part of a primary key. So if you notice, these both share, say, username as a primary key, but also order number. This physically co-locates data that's like, and if the primary key was Neil, and then the next thing was Neil and his orders, those would be sort of co-located from a storage perspective. They would be operated on by the same nodes within Spanner, or they would be, technically would be in the same split, so it would be managed by the same nodes. This makes things like co-located joins very fast and efficient. Also secondary indexes. If you remember, the original interrogation was, are there any secondary indexes, any indexes on non-primary key fields? You would turn around and now at the end would be the time to apply that. And Spanner does the same thing. If you don't have a secondary index and you ran a query on a non-primary key field, you're essentially going to get a full table scan coming back at you. So we want to create a secondary index on whatever columns are going to be interesting to our query. So I'll do a quick little run through on verifying replication. This is demo time, so this is usually when the sweat beads start. So if we could I'll cut through this.
Yep.
All right. So to be respectful of time, I'm going to just sort of run through some trivial. I'm going to create 3 keys. I'm going to deal with 3 keys in my Dynamo table. I'm going to have my add key, my change key, and my delete key. I'm just going to, so the add one I'm going to add in, see if it comes over to Spanner. The change one, I'm going to change an attribute, and the delete one I'm going to get rid of. I'm going to basically see those happen and then walk through everything that happens. So let's just verify a few things. Number one is I don't have a key. I don't have the add key. That's the one I'm about to add in. Let's look at the key I'm going to change. The key I'm going to change right now is currently set to false. And so anybody want to take a guess at what I'm going to change it to? True. All right. And then lastly is I'm going to run delete. And so there's a record there that we're going to wipe away. All right. So let's go and mess with these things on Dynamo side. So I'm in my Dynamo table. And the first thing is I'm going to just add my add key, and I'm going to add a Boolean called subscribed, and I'm going to call it false. So let's add that. And I'm going to also then modify I'm going to change this key. If you remember, it's set to true or false. I'm going to set it to true. So I'm going to change this key. And the last thing is I'm going to get rid of. So these are kind of the canonical CRUD operations, right? What would happen if I changed? What would happen if I thing? Okay. So I've changed everything on this side. So let's look at our Lambda function real quick. So our Dynamo table is set up to have a trigger. This trigger is DynamoDB spanner Lambda function that showed earlier. And this is that function. Some things I'd point out is that that function obviously needs to operate with some credentials in order to talk to the Google APIs. Those credentials don't belong in flat files or any sort of extractable measure. You're going to want to set those as environment variables for your Lambda function. And you would take the entire service account JSON and shove that in as an environment variable for your function. Let's say in this case service account. That is in fact not my service account JSON. Okay, and then let's check CloudWatch and see if any logs came through. So is that about the right time that things came through? So this was the key I added. That timestamp should be about right now. I added my key, and you can see that basically new image, string, my key, Boolean false. And then this is the key thing to pay attention to is PubSub ID. So that's the Lambda function having contacted Google PubSub and the Google PubSub API saying, here's your PubSub ID back. And basically, my change key, you can see that the old image was, or the new image is true, the old image is false. And my delete key, you can see that it was a remove, and it was removed. Okay. So in Cloud Dataflow, this pipeline is running. Actually, I should have shown that. But this is currently running. So this pipeline is consistently running. I should have shown the counts beforehand, but I missed that step. But in the logs of this, you can see that basically the logging for PubSub says, hey, 3 keys came by my way. And so what it did is it ran, for each of those keys, it ran through this pipeline. So that's already done. Let's see if we go back through. So before we had a key here, my delete key, no results found. So that's been wiped away. That was the key we deleted out. My change key, what did I change it to? True, right? I flipped it from false to true. and the other is add. And it's there. So, so that's effectively the entirety of that pipeline. It's actually a really, really simple pipeline, something you could orchestrate pretty easily. We plan to publish it as a solution so that folks can download it and try it their own. So that's it for me. I'm going to hand it over to Neil.
Let's switch this one first. Yeah, I got it.
You got it?
Yep.
Do this?
Yep. Okay, so Sammy has shown you how to use Dataflow as a streaming pipeline, making sure your changes go from Dynamo to Spanner. I'm going to do the big job, which is the bulk import, creating the Spanner instance and creating and importing all the data. So like we said, 4 clicks to create Spanner. I'm going to create an instance. I'm going to use the Music Brains, yep, spelled it correctly, database, and I'm going to configure it in my home country, Europe West 1, which is Belgium. I've actually been inside that data center. It is massive. I was expecting it to be big, but it was bigger. So we create 20 nodes. This will give us a database that will be able to handle 40 terabytes of data, 200,000 reads per second, and 40,000 writes per second. And it's bigger than what we need for MusicBrain's database, but it's for getting the demos happening speedily. Here we have our DDL, which is simple create table. You can see here that I'm using a commit timestamp on that row, and there's primary keys. I'm using a hashed ID as the initial primary key. I'll explain that in the next section. So I'm just going to copy paste this into my Spanner creation, continue, edit as text, bam, and create. And this is my 4th click. So that creates my database. And thank you. And there I have the 100 and something tables that are in the MusicBrain's database. So now I want to import my data. Well, MusicBrain's already puts all their data on their website as tab delimited format export files. So I've put all those already in a cloud storage bucket. I've written a Dataflow job, as Sammy's explained, with all the steps. And I'm now going to run that Dataflow job to pull the files in the source path from this cloud storage bucket and putting it in this new database that I've just created. So I just copy that and run it. And this simple build run step of Maven, and it started. And in a couple of seconds, it will initiate the Dataflow job to start bulk importing the data. Yep, there it goes. In theory. There we go. So this Dataflow job, as Sammy explained earlier, graph is still being analyzed. There we go. So it looks at the cloud storage bucket, gets the list of files to import. It reads the tab delimited format files, gets each line, which is a single row in the original database. We create the Spanner mutation, passing the data in that row, converting it to the Spanner types. And then because it's a batch job, I'm going to batch these mutations together in groups of 100. And then write these batches of 100 to Spanner. It's more efficient to write batches of rows to Spanner than to write individual rows. And this job is now running. Dataflow uses Compute Engine VMs, and you can see here, if I refresh that page, it's created a bunch of VMs. There we go, a bunch of VMs to run those Dataflow steps. Each of those boxes can be run on individual nodes with Dataflow managing the data, passing between one and the other. And it will alter scale high and low and it's just going now. So it's read so far 78 files, 234 files, and it's starting to read them. So, OK, we'll let that go running, and we'll come back to it at the end of the next section. So Sammy talked about NoSQL, and I'm going to have to run through this quickly because we've got less time than we thought we had. Sammy talked about NoSQL. I'm going to be talking about the relational database side import. My examples would be MySQL specific, but the general case applies to most relational databases. So Sammy's already talked about why. The advantages are reasonably obvious. No planned downtime, no ops, everything's managed for you. Operating system, hardware and software updates happen all in the background. Horizontally scaled, so you can just add more power when you want to. No sharding, you've got a globally consistent view of your data. and external consistency with ACID-compliant write transactions. Read transactions allow you to read data at a particular timestamp up to an hour old, and you've also got ANSI 2011 SQL queries. So the first thing you want to do is look at your existing schema and check the data types. Spanner has a very concise set of data types. There's just this little bunch here. All of these can be actually used as keys, apart from the array type. The array type can be of any of the other types. So you want to look at your existing schema and map the existing data types to the Cloud Spanner data types. Many of them have a direct mapping, but some of them, as you can see in this list, do not have a direct mapping. In this case, you want to change the application database access layer, like we mentioned earlier, to convert from your internal representation to an equivalent Spanner representation. So for instance, an enum, you'd write that to Spanner as a string, and you pass it back out into the enum in your application. Table keys are an important consideration in Spanner. In traditional databases, you often work with sequences, where your rows increase constantly. That is an anti-pattern in Spanner, because Spanner splits the data into multiple splits, sorted by primary key. And when you add data, it's added to the split. So if you've got a sequential key, always increasing, it'll always be added to the last split. And if you're doing that a lot, then your last split becomes the only split where there's any database activity, becomes a hotspot, and you may have 20 nodes, but you're only using one to write your data. So what do you do about this? Well, you need to prefix your keys with another key in order to distribute the data better. Now, if it was a greenfield database, you'd probably use a unique UID or a random key. But because we're importing, we want to keep this sequential key, so what do we do? Well, we add a hash. We simply do a simple hash of the original key and prefix that in the Spanner primary key. So you see on the second row, the primary key has a hashed ID, which in this case, if just on a CRC32, it doesn't have to be secure. It just has to be somewhat random, but deterministic based on the original ID. There is lots of documentation on cloud.google.com about how to hash keys and other details in which to avoid hotspots in Cloud Spanner by using this feature. Of course, if you have referential keys, you need to include the hash key in the reference because it's the primary key of the existing table, so you need to include the hashed key in the referenced table. This is to avoid a full-scale table scan when you're wanting to look up the keys when you do a join. Once the application has been fully migrated, you can do another migration if you want to, which is to remove all the sequences and switch everything to unique UIDs. Secondary indexes in Spanner are also implemented by tables under the hood. So the exact same problem occurs with columns that you've got in an index. In this case, we're indexing events by timestamp. Timestamp, of course, is a continuously increasing key, and you'll get a hotspot because you're adding more and more events, increasing in time, so you're getting a hotspot. What do you do here? Well, you do something called application level sharding, which is creating a shard ID. This is not the same as a split ID. It's just an application-defined value to mix up the data a bit. In this case, I'm using the CRC32 of the timestamp, modulo 100, which gives you a number from 0 to 99, which is relatively random based on the timestamp. I add this into the table, and I index on that timestamp shard ID, so that way the index itself is randomly distributed. If I want to select from that index using a range select, I have to include all the shards, because otherwise, again, because it's the key, Spanner will do a table scan. So again, I'm selecting using the between clause there, shards 0 to 99, and then using the range clause, and that gives a limited select and not a full table scan. Sequences do not exist in Cloud Spanner because, as I said, it's an anti-pattern. So for that, you have to implement them in your application. The simplest way is to have a table in your database called sequences with a sequence name and the next identifier. When you want to add a row to your table, you get the next ID, you increment it and update your sequences table, and then you insert your new row with obviously the hashed ID and the new sequence number. This is fine for a rarely modified table, but if you've got something happening a lot, this, of course, becomes a choke point. Every insert will have to wait on the sequences table to do the update. I've gone a bit too far for myself there. So the way to avoid that would be to get each application instance manage a block of sequences. So it would read, say, 100 sequences from the table, manage them internally, issuing the sequence IDs to itself. It means you'll lose the continuous value of the sequence to a certain degree, but as said, continuous keys are not the best plan in Spanner in any case. Foreign key constraints. Spanner gives a lot of performance benefits by trusting the application to keep the data consistent. And one of these things is not having foreign key constraints in other tables. This you can have to implement in the application if you want it, but in most applications, it already knows what data is there, what data isn't there, and so you wouldn't be able to create, the application shouldn't be able to create an object without the parent object already existing. If you do want to add foreign key constraints, you can easily do it yourself in the database access layer, simply by checking for the existence of a reference table key, and if it doesn't exist, throw an exception. And if it does, then you insert your row, and there's a foreign key constraint check implemented application side. Similarly, on delete and on update rules must also be implemented in the application because there's no foreign key constraints. You find all the child IDs that are referenced by the parent, you delete them all, and then you delete your parent. That's an on-delete cascade rule, of course. On-delete update or on-delete set null would be implemented by updating the rows or abandoning transactions should any child rows be there. As Sammy already mentioned, the interleaved parent-child relationship does have referential integrity constraints and on-delete rules. So here we have a parent and a child. We've told it to interleave in the parent on delete cascade. Sammy's mentioned in detail about that. I'm going to just skip over it. But in this case, there is a foreign key constraint, and the child table key must reference the key of the parent. And in an on-delete cascade rule, you delete the parent, it deletes the children. You can create a hierarchy of 6 levels of tables in this manner, but be aware because all the child tables have to be in the same split as a top-level row, the 4 GB size split limit applies to the size of the top-level row and all its children. That hasn't happened very often, but I have had a customer that thought that they would meet that problem. Commit timestamps are mentioned. You define them in the schema with an options clause. In the application, you use a special value to insert the commit timestamp, and then you can use that during the migration process to detect whether a row has later or earlier data. I'm really rushing through this because I can see the clock counting down quite rapidly. Other things that you'd have to implement on the application side. Default values. Easy to put in your database access layer. Stored procedures and triggers. Well, due to the distributed architecture, triggers are a bit of an anti-pattern. You can easily implement in your application, and because Spanner is effectively infinitely scalable, you don't have a worry about running triggers and stored procedures in the database. You can just have more nodes, and everything runs better. It also gives you the benefit that the stored procedures and triggers, you're putting your business logic in the application with the rest of the code, and you can have it written in the same language, you can unit test it, and without needing a test database instance. Per table access privileges don't exist in Spanner. Your access control is read or write for using the Cloud Platform IAM controls for the whole database. And finally, go back. JDBC, it's currently read-only, and there is no data modification language currently. But right at this moment, there is a second Spanner talk going on over in Moscone South, where DeepTR, Cloud Spanner's PM, is announcing that data modification language is being previewed right now, and there'll be a read-write JDBC wrapper coming soon. OK, we've got a minute or so left, so let's have a look at my demo and see if everything's run OK. So back to the Dataflow view. What have we got? So we've read 234 source files. From that, we've got 20 million records, which we're adding to Spanner at the rate of 31,000 per second, batching them, of course, down to 300 batches per second or so. And let's have a look at the logged failures. There have been no failures and 21 million successes. And just to show that this is for real, I'm going to stop this job to give my database a rest. Where are we? Spanner. Let's have a look at the artist credit table. And let's have a look at some of the data. So here, when the data finally comes out, hello, Spanner. The demo gods are not smiling on me with 20 seconds counting down on the clock. There we go. So here we see that the data has been added. The original sequential IDs have been prefixed by a hash and therefore been completely mixed up in a random order. And if I just want to run a query on that data, we'll run a simple query selecting all the recordings that have the word cloud in their name, joining them with the artist, and see what we get out. Query, bum, 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 bum. Oh. There we go, let's run this query. This, when I tested it yesterday, took about 5 seconds. Because it's a demo, it's probably going to take 10 times as long, and I can be sitting here talking to myself for 5 minutes. Yeah. So once the query comes back, having scanned its several million rows, because of course I'm not using an index key, I'm using a table scan on the name. Okay, what we'll do is we'll let that run, because the demo gods are obviously not smiling on me. We'll run through a quick last couple of slides, and we'll come back to this. So,
Sorry.
Other things to wrap up. Tomorrow, there's a talk on how Nest camera services moved to Google Cloud. They were originally on Amazon when Google acquired them, and they've just completed a massive migration. So all the camera services, all your recordings on Nest are now on Google Cloud. Niantic are going to talk about moving to Cloud Spanner. Niantic are the people behind Ingress and Pokemon Go, and reinventing databases for your journey to the cloud. In the archives from yesterday, there was Optiva, who migrated from Oracle to Cloud, and their lessons learned. Bandai Namco, how they're using Cloud Spanner, and the session that I just mentioned, See What's New with Cloud Spanner, which is happening right this minute. I'm going to restart my query because it appears to have got stuck just to annoy me. And finally, quote from Optiva, when they moved from Oracle to Spanner, they could process 10 times more transactions at 1/10 of the cost. So they're obviously very happy with migration from Oracle to Spanner. One other thing I'd just like to announce is tomorrow, which is Cloud Hero. And here is my cape, because I am apparently a Cloud Hero. It's a DevOps-style game where you race against the clock to meet a second of challenges. So I now have my cape. And if we go back to the demo, it has finally finished its query. We have a bunch of tracks with their artist, who I have never heard of before. and there we go. And that's basically covered it. We've gone a little bit over time. I'm sorry about that. If you have any questions, how much time do we have left? None.
Just find us outside. Thank you.
Just find us
Thanks for
outside.
attending.
OK.